My name is Walter Grayman. I'm representing the EWRI WDSA History Project. The purpose of this project is to document the history of water distribution systems analysis. A key element of this project is a series of interviews with practitioners, researchers, developers in this field. And we're going to be asking them their personal experiences of what they have done. Our interview today is with Martin Lambert. Martin is a professor at the University of Adelaide in Australia. This interview is being taped at the CCWI conference in Sheffield, England on, this is September 6th, 2017. Martin, how did you first get into this field of water distribution systems analysis?
Thanks very much, Walter. I guess I've had a great fascination with fluid mechanics and water engineering, basically from an undergraduate student. And I guess that really led into then working with open channel flow initially, and so my PhD was looking at the interaction between main channel flows and floodplain flows, so fast moving water and slow moving water in a floodplain. And I was really quite inspired by the person who taught me at university, Dr. Walfield, and I went on to work with him. But Professor Frank Henderson from the University of Newcastle had just retired, and Frank was sort of still working on that second edition of open channel flow, and he was really very much interested in this compound channel problem, and so he was one who sort of posed the problem, and then I worked on that during my PhD. I also had the opportunity to go to the UK to work with Professor Robert Sellon at the University of Bristol, and that involves working on model studies at HR Wallingford. And so, it was a great experience to sort of work at the University of Newcastle with some sort of eminent people in hydraulics, but also then go to the UK and to work at such a huge sort of experimental facility as HR Wallingford on compound channels. I guess once I finished working on that, I then went on for a postdoc with Professor George Kazira at Newcastle. And it was sort of a combination of hydraulics and hydrology. We were looking at this, the joint probability problem associated with sort of coastal floodplains. And that really ended up us developing sort of a model of the whole catchment, including sort of stochastic rainfall, runoff, and then flooding, and linking all that together to look at this interaction between freshwater floods and sort of ocean water levels. But during that period, there was a job that came up at the University of Adelaide. They wanted a specific person in open channel flow, and that was to work with Professor Angus Simpson, who was the pipe flow person. And I guess I had applied for that position and got it, and was able to move to the University of Adelaide. And that was just a sort of a fantastic opportunity for me as a sort of young researcher to move to that university. But also it was really the beginning of working with Angus. So I was the person teaching sort of open channel flow, he was teaching pipe hydraulics, and we had research in different areas. I'd continued my work in stochastic hydrology and rainfall modelling simulation. But there was a time when Angus was to be away on special studies leave, and he said, I've got a PhD student working on the inverse transient work with Jim Liggett. And he said, would you look after John Witowski? Would you sort of work with him while I'm away? And I said, I'd love to do that. Angus said it'd be... And I could really see there was a link between the sort of the unsteadiness that I'd worked on in the open channel flow area, so I was quite familiar with those equations. The wave speed's somewhat different, but also the experimental work that I've done a lot of experimental work in sort of open channel flow, and to then sort of bring that to bear. So really the experimental field work has been something that's been a strength of mine. To work with Angus, as well as being quite interested in the numerical model development and where we can take that. So that was really the first introduction, but it was really going with Angus and starting to work on that project with John Witowski, and he was a sort of a fantastic PhD student and colleague. But I remember going to a WDSA. It was one of the first sessions that it had at an EWRI conference at Tempe in Arizona, and that was where I then got to meet sort of the greats of the field of water distribution analysis. And it's quite inspiring as a younger researcher to go along to those meetings and start to see people who you looked up to and looked at their work, and then being able to sort of start to think about what you might do to make that contribution yourself. And so that's really how I got to water distribution systems, and really I haven't left.
What have been your major research areas within water distribution system areas?
Okay. I guess I've really focused on the unsteady flow side of things, so the transient flow, but not really the large water hammer events. And I guess, understanding water hammer and how that works within systems is key. But really it was coming back to these initial tests that we did with John Witowski in the lab, and you've got your sort of water hammer models, and you've got your numerical modelling and your inverse approach to be able to sort of back calculate where, for example, a leak might be, or a closed valve, or a blockage. But it was that going down to the lab and seeing that really the measurements that we're taking in the lab wasn't exactly matching the model that we were using. And then spending quite a deal of time trying to sort out what the issues were with the modelling, with the experiments that we saw, and how we got the modelling to match. So that was sort of the initial phase of that, and I guess it gets in somewhat better and somewhat worse when you go out to the field and you start taking field measurements, and you can always sort of see the elements of the mathematical models that you've got in the background within the traces that you see, but you start to see a lot of other things, and also some other complexities that you're not seeing just doing theoretical studies. One of those issues was the issue of unsteady friction, and just the more rapid decay that we see within the lab. And also then once you get out to the field, you start to see much more complexity of the pipe system than you were expecting. And so that's really then been the focus, and it's taken us almost, I think we've been working on this for nearly 20 years now, and we're not at the end of it, and there's a whole lot of exciting stuff that's opening up. So really starting to think about using inverse transients for leak detection, and that was the first thing. And so we did validate that in the lab. But it was really some field work that we'd done out with the South Australian Water Corporation on some of their larger pipelines, the Morgan-Whyalla pipeline. And it turned out that there was a section of that pipeline that had a slightly thicker wall. So the wall was 6 millimetres thick rather than sort of 5 millimetres thick at a certain location. And that wasn't recorded on the plan very well. And there's some older plans that showed that, but the plans that we had didn't show that. And it turned out that 1 millimetre change in wall thickness was very obvious in the transient pressure traces that we were recording. One of the key things was that when you start thinking about transients and most people start to think about water hammer and large events, and was the realisation that in the laboratory that we could actually have a side discharging valve, so a smaller discharge, almost a leak that we'd created ourselves, and then very rapidly close that leak and generate a much smaller wave that was propagating down the pipeline that would then allow you to start doing diagnosis. And that was the kind of event that we'd put in that was being used on this the Morgan-Whyalla pipeline. But it started us thinking that if we could see a 1 millimetre change in the wall thickness of this pipeline, and really clearly, it was really stood out that there was something going on over this 110 metre length of pipeline, that then maybe we could find smaller changes in the wall thickness of the pipe. And that really led us on to starting to look at using pressure transients to then diagnose the condition of the pipeline. And what you'd like to be able to do is to then essentially screen the pipeline to say, okay, this part is almost in original condition, so you could compare the wave speed or the impedance that you'd expect for this section of pipeline with the next. So is this section better than another section? And also then trying to sort of understand what else you see within the water distribution system. And I think that's one of the key things about transients, is that they're very much an active input into the system, and that you then are able to see just so much about what is going on with the water distribution system that you really wouldn't see with a steady state analysis. And I guess that then brings me to what I found exciting about this particular area, was that really almost that by actively working with the system, by actively sort of putting in these small pressure waves, seeing what was going on, you could almost forensically sort of back engineer what was underneath the ground. And one of the key things was that that you could actually find things that weren't on a series on the plans. And so, sometimes there'd be an offtake that was on a particular pipe section that wasn't able to be, it wasn't listed, but the transient would tell you that there was something there, and you'd have to go back and almost reverse engineer what the pipe system was. Even though the plans, if you've got a good set of plans, that's a great place to start. But sometimes you've got to go back and actually diagnose what is the system, and then once you've done that, come and start doing the pipe condition assessment as part of that. But I guess it was quite a long journey to get to that. So we were looking at, in the laboratory, finding small leaks that we'd put in the system. We then at one stage, instead of having a leak that was continuously running and we have a little active pressure wave looking for that leak, that we said, well, okay, let's have the leaks closed, and then we open them. And those then become bursts within a system, and starting to look at techniques that would try and find that depression that you see in the pressure wave, in the pressure in the pipeline, to determine where these bursts had occurred. And then moving on to changing the pipe wall thickness of the laboratory system so that we can then detect when there's a change in pipe class, for example. So you've got a pipe that's slightly thicker or slightly thinner, and to determine where that is. And so that was then going back to looking at the condition of the pipe wall. I guess one of the key things is that you can do a lot of this in the time domain. So when we think about water hammering, we often think about a pipe, a valve closing, and a wave travelling. But then we've also looked at frequency domain techniques in this particular area. And it soon became quite fascinating. And I guess you've got to have a fairly simple system for the ideas to work. But just looking in the frequency domain, it was that we could start to look at the frequency response diagram of the pipeline. You could then see if once a leak was introduced, you'd actually have a little pattern that would start occurring on the frequency response diagram because the leak was there. And it just led to a whole range of techniques that are very elegant. So it's sort of it's rather neat mathematical solutions to these particular problems. And I guess I found that fascinating. So the initial work was with Jim Liggett, looking at sort of the damping that you get in the transient trace when there's a leak occurring. So after working with John Vitossi on the inverse transients, Pedro Lee had done some work on the frequency domain. And that was a fascinating sort of look at some quite simple things that you can do to determine when you have leaks there, and then how do you locate the leaks from the way in which this frequency response diagram had changed. That then, at the same time as Pedro Lee was working on that and looking at sort of frequency domain techniques, we'd had an industry project with the water utility in South Australia, and another student, Mark Stevens, had started to look at that. And this was really about going out and doing field work and working on real water distribution systems. And so you had this, I guess, contrast between theoretical, numerical models, optimization, inverse, through to the laboratory work, which was telling us something, not always telling us that it was easy. And then another student who was really keen to go and work out in the field, looking at real systems. But one of the key things was to actually, how do you synchronize measurements out in a water distribution system? And I remember being out in a little town in South Australia, and we had permission to work on this particular town, particularly on asbestos cement pipes. But we'd work late at night, but we'd actually run little phone cables, hundreds of metres around the street to synchronize our measurements between the different stations. And then we went to utilising a radio signal. We'd send a beep over a radio tone to actually then trigger all the sensors to start working. It was good, but we really needed high accuracy, and also sometimes we'd be so far apart on a pipeline. If we were, say, 5 kilometres apart, we were struggling to get the tone to actually go. We certainly couldn't run 5 kilometres of cable just to do a test. And so we then went to utilising the GPS system and actually taking the time synchronisation from that, which allowed us to highly synchronise our transient pressure measurements across the water distribution system. So it was really it's been a fascinating journey of this. Just once you get to real systems, then it does get more complicated and difficult. But in some ways, they can be easier because in the laboratory, the waves are travelling at over 1,000 metres a second. in a say a 30-metre pipe, you don't have a lot of time to actually take those measurements. You get a lot of reflections backwards and forwards. So, actually going to the field makes it harder, but also easier as well.
It seems that the group that you're in at the University of Adelaide has been very successful, and one of their successes has been that they work with external groups, utilities, and practitioners. And has that been your experience?
Yeah, I think that's one of the key things. But I have to say that the group works well internally within the university, so I've really valued the people that I've worked with within our school. But also being able to work with a utility and to get access to a system to do some things. And of course you want to work within the rules of that system, but also having access, it's hard to do something that's going to help a utility if you can't ever access their system to actually to do work on it. I think having that access has been a key feature of what's allowed us to go where we have gone in the past.
You're starting to move into the smart water field.
Yes.
Can you tell us about that?
Yep. So I guess it's one of those things where a lot of what we've come up with our research is really taking a set of sensors and putting it on a pipe. So whether that could be a transmission pipe or a water network. Typically what we do in a water network would be to close one valve and essentially turn that pipe in the water network into a single pipe again. It's still connected to the wider network and everyone has water, but very much taking a series of sensors, taking some tests on that particular pipe, and then doing some detailed sort of diagnosis of what you're seeing. You then take those sensors and either move along the pipe or move to different areas in the water distribution system. But when you start to think about having sensors that are continuously monitoring, and I guess that was really some of our work looking at if you have a burst that occurs and have some pressure sensors that are monitoring the system, what kind of algorithm do you need to actually detect when that's occurring? And so that was work that we did with Dalia Smith-Eunice, who joined us from Lund in Sweden. But I guess once you then start, the sensing systems that are becoming available, we're actually able to take synchronized high-frequency pressure measurements. They could be measurements of acoustics as well in a water distribution system, and then having that transmitted back almost on a continuous basis. So the sensors are no longer taken out and placed to where you want to do a test on a particular pipe. You're actually sitting in the network listening for something to occur. And that's so either you're looking for bursts, you might be looking for events that are occurring within the system. So really starting to understand some of the key aspects of that system, and it's really a whole new research area. And I guess where we've gone to with the pipe condition is that we're moving into more advanced signal processing techniques. So we have people working with us from electrical engineering to a radar specialists, really applying higher level signal processing techniques. We're moving into looking at different input signals. So rather than just a transient step wave of a valve closing, we're having essentially pseudo-random binary signals into the system. So really we're advancing in that sort of pipe testing region. But at the same time, some of those ideas of advanced signal processing also fit nicely with a sensor that's sort of sitting there passively looking at your system and helping you understand what you're seeing within that.
Where do you see the field going in the next decade?
Right, it's one of those things. It's been a fascinating 20 years of where we've come from. I was thinking, can you spend this long in an area? But it turns out that it keeps, every time you sort of turn back, to sort of turn over a leaf of something else, there's another whole world out there to explore. And as we've moved to, I guess we've started off really looking at a single step wave going into the system and looking at the reflections that come back from that. But as we move to these higher frequency, more continuous input signals, and so what's happening is that you can increase the input of the bandwidth of your input, which then allows you to, if you can have a higher frequency, higher frequency input, you can actually then see more and get more resolution of what you're looking for. But as you move to more higher frequency signals, you then get more dissipation. You need better algorithms to actually diagnose what you're seeing. So a good example is you put in a step wave, you get a step reflection back, either from a wall condition change or a junction in the system. But if you're putting in a continuous, really complex signal, you actually need some quite high-level techniques to actually interpret what you're seeing. The other thing is that a lot of leak detection systems are very much acoustics based and really sitting there passively listening for leaks, for example. So you're very much listening with an accelerometer for a change in basically the noise in the system. Whereas what we've been doing is really an active approach where we're actually putting something into the system and then looking for a reflection off a leak or a reflection off a change in the wall. And I guess that's another fascinating area, is to sort of start to bring the two of those together, where what's the difference between an acoustic signal and a pressure signal, and also then once we move to higher frequencies, the differences between the two become sort of not as big as they were when you have a large pressure event versus a sort of a low magnitude acoustic event, higher frequency acoustic event. And so it's really sort of merging those two fields together. And again, bringing in more advanced sort of techniques and ideas. One of the key one is to start to think about different ways of doing sensing. And one of the ideas I've been quite excited about with what we've been doing was to actually have a series of dual sensors or a sensor array. And what you can do with that is to be able to instead of measuring pressure, which is a single value that you measure, what we're able to do is actually pressure is actually a combination of travelling waves. So you could have, for example, if you're looking at a pipeline, you have a wave coming from the left and a wave coming from the right. Those two pressure waves sort of add together to give you the pressure that you're measuring. And so what we've been able to do is to actually have two sensors or a sensor array where we actually start to pull apart a single pressure measurement. We can pull apart into the travelling waves that are going in the different directions at that particular location. So you can imagine if you can do that at another location, then all of a sudden you can actually isolate sections of pipes or sections of systems where you can actually take them out of the larger water distribution system and just know exactly what's going on within that. So I guess there's a whole world of work to go in terms of more advanced sensing systems, more advanced algorithms, but also then how do we bring that into the reality of using it on real water distribution systems. And I guess that's been one of the key things for WDSA, is that you basically at a conference with people that work in that whole spectrum from sort of the theory through to the practical implementation.
Fascinating. Anything else you'd like to add?
I guess I just thinking about where we go in the future, and often we're looking for a one solution to our problem, and I think in the future it's really going to be that we've got to bring to bear a range of different solutions, particularly on the pipe condition assessment issue, is that there's not probably one technology or one technique that is actually going to solve everyone's problem, but we really should be looking at how we can bring different techniques to bear when they're appropriate. So you might have one technique that's quite good at sort of screening and giving an overall picture of the system, and you've got other techniques that actually start to look in more detail and give you more information about areas that you've identified that you need. And I just think that that's sort of something for the future, where we need to not just be focused on one idea, is to bring a range of things and actually have them feeding into each other. So that this test might actually give you information about that method that then gives you a better picture. The other thing is just, I guess what I've found fascinating about transients is that I've actually got to go out and touch the system and work with the system. And even though that is difficult, what can happen is that you learn a lot about what is going on in the system. And so that's something where that knowledge that you get can be valuable, but it comes at putting in some effort as well.
Well, thank you very much for the interview.
No problems. Thanks, Walter.